This is just a video explaining some of the math we had to go through. This is a page containing just some scribbles of stuff we had to do. So at the top you see 44 kilograms equals H2O, which is water, and 99.78 kilograms equals NaOH, which is sodium hydroxide, which is basically sodium lye. And then below that you have 61 kilograms of Al, which is aluminum. And this is for the equation to produce homemade hydrogen. If you mix the water, the lye, and the aluminum, you have an exothermic reaction, which the lye just helps break down this coating around the aluminum, and then the water helps break down the aluminum, because aluminum is very reactive to water, and then the production is hot hydrogen, and it's hot because it's an exothermic reaction. But that was for 100 kilograms of lift, so we had to figure out how much we needed. So we had to break that down into how much for 1 gram of lift. And to do that, you would take your amount of lift and divide that by the amount of materials you needed. So to figure out how much water we needed, you would get 100 or 100,000 divided by 44,000, or you could do 100 divided by 44 and make it thousands. Whatever. So you'd get, because the thousands cancel out, so you'd do 100 divided by 44, and you get 2.27 repeating grams of water for 1 gram of lift. And then you would do 100 divided by 99.78, which is 1.0022048,507 grams of aluminum for 1 gram of lift. And then for your aluminum, you do 100 divided by 61, and you get 1.63944,203 grams of aluminum. And then we had to figure out how much we needed to produce enough hydrogen for us, which would have been 4,000 grams, I believe. So to do that, we had to take our amount for 1 gram, and since that is all 1 gram, you can just only do one side of the equation. So you just take your amount of materials and do, for water, you do 2.27 repeating and multiply that by our 4,000, I believe, and you get 9,080 grams of water, which is 20 pounds, 20.018 pounds, by the way. And then for our lye, we would have done 1.0022048,507 grams, multiply that by our 4,000 grams of lift, and we get I think that says 4,008 grams, which is about 8.8 pounds. And for aluminum, we would have done 1.6389344,203, and that would have given us how much aluminum we needed, which would be 6,557.38 grams of aluminum, which is 14.5 pounds rounded to the nearest tenth. And this is just a page with the same thing, but we have our payload, which is 1,681 grams, and our balloon was 1,000, and we needed 1,319 grams of positive lift, which would have given us 4,000 grams of total lift. And that's just kind of the measurements we had to use for the calculating the hydrogen. So this is how I figured out its max altitude. What I did was, so I went through the video and I figured out I went through the GPS log. I didn't do every single one, but I did most of them. Just kind of jotted down altitude and time. So you can see it just goes 249, which is feet. And that was at 7:16 with 51 seconds. That was when we launched it. And then the next log would have been at 430 feet at 7:17 with 10 seconds. And then the next log was 1,253 feet at 7:17 with 49 seconds, blah blah blah, and so on. And then there's another page here with just the same exact thing continued on. And then this very last one at 7:52 with 5 seconds is when it leaves cell range and is the last log. So what I had to do was I had to go through and had to figure out the feet difference, which is that top small number in between every other log. So like in between 249 feet and 430 feet, you have 181 feet, which is the difference between 430 and 249. And then I had to go through and figure out the time difference between the two logs. So the time difference between 7:17 with 10 seconds and 7:16 with 51 seconds is 19 seconds. So what I had to do was, so then you get that, and I had to go through and do that for every single log. As you can see, there's a lot of them on both pages. And then I had to convert how many feet per second that was. So I would just take the feet and divide by seconds. So for this first log, I did 181 feet divided by 14, and you get 9.526 feet per second. And then for the second log, I did 823 feet divided by 39 seconds, and you get 21.103 seconds, or feet per second. And I went and did that for every single log on the front and back page of this. And then I had to go through and add all of these up to average them. So I did 9.526 plus 21.103 plus 12.611 plus 16.187, and did that for every single one of these logs. And I divided it by 24 because that's how many logs, or how many numbers there were. And that gave me 17.712 feet per second on average, which then, when converted to meters per second, because that's what most calculations are done in, is 5.42 meters per second. And that is really good, because we were shooting for 5, so I think that was pretty good for the first time. And I had to do the same thing on this page, but this is whenever it re-enters cell range on the way down. So I had to take the altitude, which for this first one was 5,718 feet, and its time, which was 9:16 with 21 seconds. And then I just did that for every single log. There weren't many on the way down. And I had to redo that. This side was way easier because there was like a quarter of as many. And then you got the feet, or the foot difference, which for this, in between the first and second log, was 587 feet and 32 seconds. And I had to get that to feet per second, which I just divided 587 divided by 32, and you get 18.344 feet per second. And then I did that for all of the logs. And then I had to go through and add all of those up and average them again. The way I averaged, the reason I wanted to average it, instead of just do like the first log and the second log, or the first log and the last log, do the math on that and be done, was because it changes, the ascent rate will change depending on the altitude because of like air density, atmospheric pressure, all that stuff, gravity, all that. So I just averaged it throughout as much as I could to get it, kind of get it more accurate, I guess. So I did all that, and then I had added it and averaged it, and then that got me 23.671 feet per second, and converted is 7.215 meters per second, which is way faster than we were expecting. We were expecting it to rise and fall at the same rate of 5 meters per second, but clearly we were wrong, because it's about 2 meters per second more. And right here, at 9:17 with 54 seconds, it said, the GPS said it was going 50 miles an hour. That's pretty freaking fast. On this next page here, you just have what I used to get the max altitude. I had to go into the video, figure out exactly where it pops, which is at 1 hour and 41 with 38 seconds. And then I went back and I used the ascent rate, which was 5.42 meters per second, and I multiplied that by however many seconds 1 hour and 41 minutes and 38 seconds is, which is 6,098 seconds. So you multiply 5.42 by 6,098, and you would get 33,051.16 meters. So you had to convert that into feet, which is 108,434.5643 feet. Just to help, just kind of bump it down a little bit, because there is that, it changes ascent rates as you go up. So we just we rounded down to 5 meters per second, and you'd get 100,000 feet and 100,032 feet, which is where it popped. And here we just have a little bit of notes I had to take along the way on my phone. We had to figure out, for the first one, we had to figure out how much hydrogen we needed, since we were making it our own, and based on a couple of Google searches, pure hydrogen can lift about 32 grams per cubic foot. So we were thinking ours would be, this was like a really, we were thinking this was going to be, this was a high guess. It was 90% pure. It could lift 28 grams per cubic foot. So using that, you would need 60 cubic feet to make it float, and 143 cubic feet for the amount of positive lift we wanted. And then after that didn't work, we had to go back and redo it for helium. And based on a quick Google search, helium can lift 30 grams per cubic foot. And since it was bought for us, it was already pure, so we could just use that straight out of the box. And so based off of that, we would need 57 cubic feet to make it float, and 134 cubic feet for the amount of positive lift we needed. And the helium Matthew's grandpa bought for us was not 125 cubic feet. That's what Matthew told me, but that was way wrong. He got way more than that. I think we had a good 200 cubic feet, maybe? I don't know. We had a lot of extra. And it's Matthew's grandpa, not Dad, by the way. And so the amount of total lift needed was 4,000 grams. That was using this balloon calculator that's on your screen. That was a huge help. It didn't have our balloon, but we did a lot of guessing, and it seemed to work out okay. And then down here we had the hydrogen production, because that was important for the first one also, and I already showed y'all that. That's just writing it down so we remembered that. And the only thing you can say on your screen is how we got the distance to horizon based at 110,000 feet, because that's what we were hoping for. And it, I guess it went close to it depending on how you look at it. If you don't throw in the adjustment I made, it did go to 108,000, which is close enough. But according to a Google search we did, or actually multiple, you can find the distance to the horizon by doing 1.22 multiplied by the square root of the altitude. So at 110,000 feet, it is supposedly 405 miles of the horizon. We thought that was pretty far, and it'd be pretty cool to see that far. Hope y'all enjoyed. If you have any questions, be sure to comment or ask me. I would love to help y'all out.